Okay, so now we have our lecture, but before we actually start the lecture, I want to make some introductory remarks. Ion optics years ago was the field of experts. They would design the beamline, the spectrometer, and then leave it up to the experimental physicists to work with it, calibrate it, etc., without really knowing how this all came about or running the code they actually used. Those days are over. We have the systems are nowadays so complicated, like SECAR or St. George or fragment separators, magnet systems you will see here, that even if you want to operate or use it for an experiment or analyze your data, you need the support of the program. So we will provide you with the introductory in how ion optics works, and we will then show you on the example of St. George or SECAR, and that is probably your prime interest. We will provide you with the information you need or the code you need, etc. So my knowledge comes from many years of commissioning, operating and developing systems, and I know quite a bit, but nobody is perfect, so maybe not all your questions I can answer, but we will then work on that. Ion optics itself is a model, so you can think of it as a theory which you can play with, work with, program without knowing much about reality. That's not our situation. We will use the ion optics model to describe a real system, and there comes, of course, the problem with if everything is perfectly modeled or not. So a realistic model is what we are striving for, but maybe not always available. Last remark, this is a school, not a conference, where there are well-polished presentations. So you are invited to raise your hand, ask questions, and make sure that we are not losing you in the process. We are progressing quite quickly. So if something is there that you didn't fully understand, or at least in principle, let us know. We will correct that. So with that said, we are now going, and you see my laser pointer, I hope. This is, no, not yet. Now you can see. So this new feature, I don't need this instrument anymore, only as a backup, but you can follow where I'm pointing at, I guess. So there will be, this is called the separator ion optics school, where separator refers to recoil separators, not fragment separators. So I will be providing 4 lectures, interactive lectures, hopefully. Today, the first one, Manuel Kuda will give tomorrow a lecture. He has obligations, as Hendrik said, of teaching at Notre Dame. So he will be here in the afternoons for the online sessions, but not every morning. As I mentioned already, in the afternoon, there will be hands-on sessions where you hopefully will have COSI running. Now, who has COSI not running yet on his laptop? So everybody, excellent, very good. The motivation. Okay, the motivation or the field of ion optics is the manipulation of charged particles. So like electrons, ions, like protons, neutrons, alphas, heavy ions, anything that has a charge. So we are not dealing with the optics of photons or neutrons or other particles that have no charge. The field will be beamlines or beam delivery systems, or magnetic and electric analysis systems, separation for experiments. We will not talk about acceleration of ions. There's an ion optic field at great laboratories like CERN, Fermilab, Brookhaven. They design new systems for new energies. we will not change the energy. We will just analyze the particles like an experimental facility, if you want. So ion optics is, of course, one particular field, but if you really look at it, you need more programs to support, do experiment. You will, of course, need more. So I just have a list here. You need, for the floor plan, for instance, you need some kind of a CAD system. I use AutoCAD, but there are other programs which you can use to make sketches or look at the layout, the floor plan. You need some knowledge of linear algebra. We will introduce everything, but if you're not familiar with matrices, that may be difficult for you, but I assume you have. In first order, these are matrix calculations. If you go to higher orders, then you will find the word map in COSI program. You can think of it still as a matrix with extended higher order terms specifically built in. So for the higher order calculations, of course, this cannot be done by just calculating matrices. You really need a code, and there are many codes available. We will be using COSI Infinity, not only because Martin Bertz, the creator of this program, is here in-house, but it's also very flexible. It allows you to, it's basically a program. So whatever you calculate, you can immediately use it and program, get a number out as you want with an equation. There are other programs, just if you are familiar with them or you come about them, like GEOS, Ray Trace, etc., many other programs. The ion optics code will use fields. So we are not in the teaching here how to create fields, but field calculations are a part of a whole project. So people who have designed a system like that, they have probably done field calculations. Like Poisson, the old program for many years. Opera is a commercial program available here. Magnet, there are many others. These are typically finite element codes. The Maxwell code is becoming more and more popular here, so you may have heard about that program or actually doing calculation with them. So you need the properties of the incoming particles, or if you have a target, there's some kinematics involved, so you need a kinematics code. You will learn about charge distributions, which is important in recoil separators, energy loss in targets. So there are other programs like SRIM or LISA++, which you may need to supplement or provide information of the system if it's not yet already built. Many other specialized programs are feeding into the ion optics, like synchrotrons, cyclotrons, which are accelerators, and we are not talking about those here. Gas-filled systems, I will say a few words to that. And for Monte Carlo simulations, of course, we are not covering them here in this course, but they may, you may come across those or have a need for those later on. I've listed here some literature. I call Hermann Wollnick's code my Bible. He has comprehensively included from the very beginning many issues that are mathematically involved, solved here and well presented. But there are other codes historically to honor those people who have worked before hard, but also codes that provide specific information that you may be looking for. The old Bible, if you want, is the code from the late Carl Brown, who has, in the 80s, provided this book. It is now online. I'm not sure if you have it on the wiki, but anyhow, it's easy to find. If you write transport, then you will find this code online. So, what drives the ion optics are, of course, the forces on the ions. So the Lorentz force is the product of the charge Q times the field plus the field by the magnetic field, the charge times the velocity times B. So that is the basics why we can manipulate ions completely different from what in ion optics is, where you have refraction and reflection on optical surfaces. So we need the electric field. You see that the force is in parallel to the electric field. So if for acceleration, you need an electric field. The magnetic field is, because of this cross term, never changes the energy or the momentum of a particle, because always perpendicular, which is nice for analysis where you want to know the properties of the beam and not necessarily accelerate them. But as you will see, in the recoil separators, we will also need an electric field because otherwise we cannot get the mass separation that is the issue there. So if you look at the dipole field, and here in this region there's a dipole field perpendicular to the plane, then the particles will go on a radius, which you can easily see by putting the magnetic force here perpendicular, so it's just the product, equal to the centripetal force, and then you get that the momentum is proportional to B. This is very convenient to analyze particles, because now for a given field and a given charge, the momentum it changes the radius. And if you have here a detector, you have a dispersion, a momentum dispersion, and that is used in spectrometers, as you all know, to analyze and determine the momentum and also then the energy. In the old days, the magnet, the dispersion was always referred to in momentum, but COSY uses the energy. So a parameter, the energy is of course not independent of the energy you are, but the momentum is. So what we learned from that is a general rule: if you change the momentum of a system and you want to have the same ion optics, so the same particle flow through the system, you need to change every magnet by the same ratio. You change the momentum, not an energy. So if in COSY you calculate for another energy and you want to study the ion optics, you need to calculate the momentum ratio and then change the fields to that. That is a practical consequence of this. So now let's discuss what a ray is and what we do with the ray then. A ray is here from the beginning of an ion optical system to the end, location 1 and location 2. And in location 1, you would define a ray as something which has, in the transport notation, 6 parameters, that is x, theta, y, phi, L, and delta P over P. So x and theta is in this plane, in the coordinate system, z is in the direction of the beam, x to the left, and y vertically. That is what is used in ion optics as we know it. The accelerator people will actually use a different coordinate system, so don't get confused with that. That is an unfortunate historical inconsistency, but you have to know what it is. So when we are talking about the z direction, it's in beam, x to the left, and y up. So x, so a ray which traverses here the location 1 plane is x, then you have the angle theta horizontally, and y is vertically, and L is a parameter which we are not dealing much with about unless you come into timing questions. It is the difference of the central ray to the actual ray, the length difference, and of course that can be converted via the velocity into the time difference. Delta P over P is the last one, of course not represented here. Now, this was good enough when you were dealing mainly with proton accelerators, but not good enough, of course, for what we are doing using ions. We change the mass, we change the charge. So COSY has already recognized that and built in 8 parameters. So COSY we will have to do with 8 parameters. One thing I should mention again, all these parameters are relative to the central beam. So the central beam has a certain direction, the central beam has a certain energy, etc., and everything is relative to that. So not the absolute angle or whatever, but all relative to the central ray. Now what COSY adds to the parameters in transport, the simple version is the mass, so dm over m, relative to the mass of the central particle, and the energy. And of course, delta K is for us, the change of the energy. So concerning the notations, already here you recognize that the notations are different. They're x, theta, and parameters 1, 2, 3, 4, 5. This is also historically grown. It doesn't make sense for me to stick with one particular. I will change because anyhow, all the sources that you have will have different notations. So you have to have an understanding of what is meant. And throughout the course, I will point that out to you, so not to confuse you. Now, here the location is 1. And we would like to take a ray, which you know now is in this approximation just 6 parameters, to a location T, or whatever you call it, the same parameters, but at the end of the system. So in general terms, if you make a transformation from here to here, you can do that with in linear approximation with a matrix, with a 6 by 6 matrix, and you have here the matrix elements. So in order to get xt, you multiply r11 times x0, r12 times theta. There are some zeros here. The x r16 times delta if you have dispersion. And these terms are in the transport code called r12, r11, r12, r16, etc. You will learn the other notations on the next slide. So this here is, of course, called the magnification, because if you change x at the beginning, what is the change x at the end, and don't change anything else, then you get the magnification. This is called the focusing function, and you will immediately see in a minute in the visualization why this is so, and this is called the lateral dispersion. There's also angular dispersion here. You will see that there are a lot of zeros in the general transformation, linear transformation. Of course, they are not zero, but then you have odd magnets. We are not building odd magnets, but we are building nice dipoles with quantum fields, and you will learn all of them, and they make, hopefully, if well designed, a lot of zeros in this otherwise 36 element matrix. In COSY that would actually 8 by 8, 64 matrix. You see also here, this is a sub X horizontal plane, and this is the vertical plane, and there are some other elements here. So this is how we, okay, I mentioned that. Now let's look at some matrices. So you may be wondering, if we just let the particle drift from one location to the other without any force, and there you have already the matrix here. It is a unity matrix. That is a matrix with the first diagonal all ones. That wouldn't do anything. But even the drift does something. Of course, you know, if you drift a particle to the central ray, it will just stay on the central ray. But if you open up an angle, it will end up somewhere else, even if you don't have a force. And that is provided by this parameter L. A quadrupole would look like this. So you have these matrix elements decoupled horizontally and vertically if the magnet is properly aligned. And of course, the length goes into it, the gradient goes into it, sometimes measured as in COSY, the field at the pole tip or at the radius. So these are examples just to show you how these matrices are. And for the simple ones, like in transport, you can, by geometry, figure out how to do them. For higher orders, you need to do something more elaborate and probably run a code to find those. So now we have for drift and the quadrupole, but now we want to look at a more complicated system. So say a beamline with many quadrupoles and possibly dipoles. So what do we do? At the beginning, you have X naught, and then you know already if you have the first element represented by R, then you would have the exit, at the exit. Now, if you have here, this here at the exit, and you add another element, then you can get the ray at the exit of the second element. So like this, subsequently, you can multiply matrix by matrix, and I hope you know how to multiply matrices. If not, also not a problem, because the code will do it for you. But anyhow, what we want to learn here is, despite the fact that we have a long system, many dipoles, many quadrupoles in first order, ultimately, the product of this is just one matrix which looks very similar to the matrix like this. So if you're confused by all these many elements, think of them just as one matrix. And if well designed, with many zeros. So that may help you to understand, and we will apply it later on when we learn about dispersion matching, etc. So complicated system, but one matrix. So now we want to get some geometrical interpretation of some of the transport matrix elements. First, the notation. You learned the notation x, theta, y, phi, and R11, R12, the matrix elements is numbered. But there are others. Wolnik uses the following notation. So instead of R12, he says x, a, is written like this, where the second parameter, the angle, is here 2 and here a. So that is at the entrance. So the second parameter is a parameter at the entrance, and the first parameter at the exit. So this here would be, physical meaning would be what happens with x at the exit if you change the angle at the entrance. Now this looks like a differential, but it's not at the same place. It's at the entrance and at the exit. That is important to know. It transports something. So that is a transport matrix element. So if you look at this here, what happens at the entrance with x, if you change the exit, it's visualized here. You just change at the entrance of the system the angle, nothing else. So no momentum change, no x change, just the momentum. And if you end up at the exit of the system, that x isn't changing, then you have R12 or XA equal to 0, and that is a focus. So this element 0 means you have a point-to-point focus. Now let's change the other way around. So change x at the beginning and a at the entrance. So a at the entrance, x at the entrance and a at the exit. So if you change here, and there's an example given where only x changes, no angle change. Here, a particular angle is just fixed. And if the angle at the exit doesn't change, then you may get something like this. So the element R21 or the matrix element AX, 0 means you have a telescope. So parallel to parallel optics. So sometimes you will hear parallel to parallel optics, but you have to understand it's a particular matrix element to 0 if you want to deal with that numerically, einoptically. Another is XX. Now, some people who don't know anything about einoptics, they cough at this and say, well, what does it mean if x divided by x is 1? Well, x, this second one is at the entrance, and the first one is at the exit. So you know it now, and you have a better understanding that XX means the following. If you change here x, nothing else, x doesn't change here, then you have something like this, which is called parallel to point optics. The same way, if you change the angle at the beginning, the angle doesn't change here, it's point to parallel. So we will learn a lot about achromatic systems. An achromatic system is a system where the dispersion, R16, or this term here, and the angular dispersion is 0. So in the matrix that I've shown here, if these two elements are 0, then it's called an achromatic system. It is not only the dispersion is 0, but also the angular dispersion is 0. Not to be confused, and that is an important distinction you will see in applications later. So, any questions? Yeah.
I don't understand the second example.
Right.
Angle, no. Can you go back to the previous slide? Too forward.
Which slide do you want me to show?
You just explained.
The one you were just on.
This one?
Nope, keep going.
One more.
One more. Yeah, that one.
Oh, that one, okay.
The telescope.
Yes.
The angle changed.
Well, it's meant to.
George, can you repeat?
It's parallel to parallel. The angle can change, yes. But it's still parallel to parallel. While parallel to parallel, the angle changes, but it's still parallel. That is what is meant.
It doesn't change relative to the reference, or
yeah.
Central.
What you're saying is here it's alpha 1 and here it's alpha 2. Yeah, I think it can change that angle, but they're still parallel.
It doesn't matter how you change the position of X in the entrance, you're going to get the same relative angle. Right?
I think so.
George, can you repeat questions just so we get it on the recording when people ask you?
Repeat the question?
Well, because the recording can't hear Fernando at the back of the room.
The question was, if in a telescopic system, the angle from the entrance and the angle from the exit can change, and as you can see here, alpha 1, alpha 2, it can change, but what means point parallel to parallel, if you have a system where you have parallel beams coming out parallel, that is called a telescope. Any other questions? Yeah, please.
Is it not, so A and X are defined in terms of relative to a reference orbit? Right?
Correct.
You call it the central orbit?
The central ray, we call them central ray.
So, correct that the angle changes, but since it's defined in terms of the central ray, that's why AX is 0, because A and X are in terms of the reference.
Well, so the question was, if this comes from, because it's relative to the central ray, I'm not sure about that.
The central ray for this element would come in, say, at alpha 1 and come out at alpha 2. That's the
The-
central ray.
Yes.
So AX, which is defined as relative to the central ray, would be 0.
I think it's because, so it's parallel, right? So you can come in at different positions and you're gonna get the same angle out regardless. Right, so your angle's in the numerator there, right? So that's not gonna change based on a difference in position from the entrance.
This is just one example. If you have here, this is the central ray into a quadrupole, of course, going straight through, not bent like in a dipole. But if you had here lines parallel to the central ray, which is not here because alpha 1 is different than 0 in this example, then you would have here rays which are going parallel to the central ray. Okay?
Getting them at the same angle regardless of which position you come to the other.
Anyhow, in practical terms, it means if you have a parallel beam coming in and you want to make sure that it's parallel coming out, like in optics, you know why we build telescopes, to magnify the image. So then you need to make sure that this term AX is 0. Okay. Now, if you want to know under which conditions some other parameters play with it, then you take COSY and just run it and see what happens instead of looking here for a perfect definition. So this is just one example that it's not only for particles that are parallel to the central ray, they come out parallel, but also at a different angle. If they come parallel but different angle, they come out parallel here. But if that is the same angle or not the same angle is a different question, I think. Okay? Any other questions concerning the definition, please?
Is AX the same as R21?
Correct. This comes from, and I mentioned that that these notations are all over the place. You see, I should have given you here the example. This is the term XX. This is the term XA. This is the term AX. And this is the term AA. It comes from here. Transport calls it 1, 2, 3, 4, 5, 6. The physical meaning is more like X theta, horizontal angle, Y theta. But Volnik and the code, they use XA, YB, L, etc. The answer to your question is yes. XA is the same like R1, 2, but that A is also the theta, which is the physical meaning, the horizontal angle. So for the horizontal angle, you have the parameter 2 in transport, you have A in Volnik, and you have the physical meaning is often called theta, the horizontal angle. Okay, so you have to reconcile, because the literature is all over the place, you need to know this. Otherwise you get confused and you don't understand what the paper actually means. Sorry for that, but I cannot help it. Is that clear that we have here different notations? If you just have a casual conversation, of course, nobody cares what you mean, but if you really want to do ion optics, you need to know this here very clearly, and you have to learn it. And I will often remind you when we do that. Okay? So let's move on, and let's see now, we know how to take a ray, define it, and run it through a system. And if you have that matrix, and codes will give you that matrix if you don't have it, and calculate of that particular ray, where it ends up at the end of the system. But you say, well, one ray, we have millions of rays if you have a beam at more. Let's look what that means. If you plot here in the two-dimensional subspace, so just look at the horizontal space x, theta, and this theta is the A of Volnick and the parameter 2 in the transport notation, okay? If you plot this here at one location, so we are at one location, not two different locations, x and theta, then one ray in this subspace is just one dot. So if you have many rays, they're of course not all on top of each other, cannot be, in particular if they're fermions or charged. You have many rays, and in this plot it would be a scatter plot. Now they can, for bad beam, they can look like anything, but one approximation is that they can be circumscribed by something like an ellipse. So they are scattered here, but they represent, let's just say for the sake of this model, they're circumscribed, but you could say make an ellipse so that 90% or 66% are inside. That is up to you to define, but ultimately, let's say it's an ellipse. Now, you know the ellipse equation. It is defined by, of course, x theta, and then matrix elements, sigma 2, 2, sigma 2, 1, sigma 1, 1. And you can actually form a matrix, this matrix here, where the parameters are, and the second diagonal here is identical. So if you write it sigma 1, 2 or sigma 2, 1 is the same. So you can use this. If you then use the column vector, x theta as x, and the transposed vector, which is a row vector, x theta, then you can write the ellipse of the matrix in this matrix form, where sigma minus 1 is the inverse matrix, which you can create from there to there by doing this. And the epsilon is a very important number. It is a determinant of this matrix. So you divide here by the square of the determinant. And then if you make this calculation, you will come back to this. So it's identical if you write this here or this here with these definitions. Now, epsilon is called the emittance. The emittance epsilon is a very important number. It is constant for conservative forces. So conservative forces do not change. This comes from the Hamiltonian description. It does not. It's called Liouville's theorem, and it is. I write here a precious commodity because it's very easy to blow up the emittance by just putting a thick degrader in it. The emittance will become big, but it's very difficult to get that back. The emittance can be decreased if you accelerate particles. So if you accelerate a beam from 1 MeV to 10 MeV, the emittance will shrink inverse proportion to the momentum. So, but of course, we are not doing that in a spectrometer and a record separator, so we cannot take benefit of that, and we have no means otherwise to do it. These dissipative forces, which can either blow up or shrink, let's say we want to increase in gases or residual gases, targets, or anything that is in the way of the particle, as you know. But you could, if you want to shrink the emittance, use electron and stochastic cooling and laser cooling. These are $1 million projects. The low energy antiproton creation, which was done at CERN maybe 20 years ago, was done with laser cooling, stochastic cooling, but laser electron cooling was at IUCF for the first time also done. These are complicated devices. You cannot just put something small in and cool the beam. So we have to be very careful. We have to know the emittance, and we have to be very careful to preserve it and not increase it unnecessarily, because we never get that back, and that will make the beam larger, the magnets become larger. So that's why I call it a precious commodity. So, of course, I should mention here, the ellipse is just a mathematical abstraction. It may not have anything to do with your beam, so you need to look if you do emittance calculations with the ellipse approximation, that your beam is roughly like that, and I will show examples where it is not. But let's do this first. Of course, at the recoil separator, we have low intensities, so charge effects are probably not effective here. But if the particles are too dense here, you don't need any degradation by dissipative forces in the foil. The particles will just slowly grow apart, and for high intensity, high energy accelerators, this is an issue. So just remember, charge effects may affect, but maybe not in our particular case where we are interested in recoil separators mainly. So now, if you don't know the emittance, you have several methods to do it. If you have a quadrupole and a drift afterwards, so Q and L, a quadrupole and a drift, then you can measure the emittance as follows. X max, which is the maximum image which you could look at a viewer or a detector if the count rate is not too high, or viewer, and you measure X max, then it depends in this form of the matrix elements sigma, of the ellipse matrix elements, L, which you obviously know because you know how you put your detector, and G is the gradient, which is a normalized to the total momentum, the gradient here, and the length of the field. So you can change this. So you have only one measurement. Of course, you have no way to deal with x11, x12, and sigma 11, sigma 12, sigma 22. But if you take three measurements, so you change the gradient, you create an independent equation, and you do that 3 times, then the system is determined. And since you know solving equations, you can then determine from these 3 measurements what the sigma matrices are, and then you know the emittance by calculating like this. So this is a way of doing it. In the exercises that you will have, you will solve a problem like this, but you will probably take more measurements than just 3. Then you get something like X max is a function of G, of the gradient of the quadrupoles, and it will be parabola or something similar like that, and then you can get a more precise measurement just with 3 measurements here. There are other methods. If you don't have a quadrupole, just measure at 3 locations the X max at location viewer 1, viewer 2, viewer 3, with the drifts between them here. Then you get 3 equations solving the matrix transformation, and that can give you also the emittance, because this here allows you to calculate that sigma 11, and if you put sigma 11 then in these 2 equations, then you can solve them all as you are familiar with. Of course, this requires that you set up a particular location where you have the 3 viewers. We won't have that normally unless you specifically put it in. So the quadrupole methods is probably more practical, because you always have a quadrupole somewhere, and a drift to a viewer can be provided. So this is probably the way to measure the emittance of the beam of whichever particles you have. So one more remark to this. You know now that the sigma matrix describes the ellipsoid. In the famous theory of the alternating synchrotrons by Courant and Schneider, they dealt, of course, with ellipses too, but they gave it a different name, the so-called twist parameter or Courant-Schneider parameters. You may have heard about them. If you venture into accelerator books and design, then you will see these parameters, so they're related. This here is times epsilon, and these are the so-called twist parameters. Just that you don't know when you see these, they're the same than what we are describing here with our sigma matrix. So now we know how to measure the ellipsoid or the emittance, if you want. Now let's look in the most general case, and let's take a 6-dimensional sigma matrix as and that can be done for any matrix. But let's do this. Then we know already how to transport it from location x0 to x1. So this is a vector of ray at the entrance, vector of the ray at the exit, and R is the matrix. Now this doesn't work only for one element, but this can be a very complicated system, but just one matrix. So don't get confused because there are many elements in the system. It's just one matrix and hopefully many zeros. So if we take now an ellipsoid, in this case now 6-dimensional instead of the 2 dimensions I just showed you, then you have, of course, from the vector x, then you have this description as the ellipsoid description in matrix form. If you enter now the unity matrix, which is matrix R times the inverse, and then you get that matrix with all zeros except for in the first diagonal ones, and you enter them here, you rearrange them, you come again to a new ellipsoid where it is defined now from the matrix at the beginning to the matrix at the end, and you take the transposed matrix R, and here the matrix, and then you have a new ellipsoid. I hope I told you that the transpose matrix is where you, where you just change the columns and the rows. So that's what you have to do mathematically. So, conclusion, knowing the transport of matrix R that transports one ray through the ion optical systems using the equation 7, you can now also transport the phase space ellipse or ellipsoid in more dimensions than 2, describing the initial beam in this way. So that is done in the transport formalism. COSY can do it. We seldom make a use of that because we're not designing beam lines, but we have different questions. So the equivalence between the transport of one ray and an ellipsoid is here. Now, to get a little bit a better feeling of what the transport of a ray means for the phase ellipse, if you have an ellipse, an upright in the x theta at one location, so don't confuse it with a transport matrix element, this is at one location, and you plot here x and you plot here theta. then you may have an ellipsoid. If that ellipsoid is here upright, we call that a focus. A focus has, even at zero location, you have some rays outside. So in a mathematical sense, if you had only rays which go like a focus all the time, then of course there would be only one ray 1 and 3. So ray 1 and 3. But that is never this case. You always have some physical extent. So you have a slit or something like that. You consider that a focus, but of course it's not a mathematical zero. So an upright ellipse is a focus in practical terms. And also shown is here the circumscribed rectangle, which normally is given by a slit will do that, but the beam is more probably an ellipsoid than a rectangle, but it's still shown here. So you can make the relation between what you see here from one point to another point by taking these rays. Now you drift coming from this location to this location, that's shown here. You do not change the rays 2 and 4. 2 and 4, they're staying here, but the rays 1 and 2, because they have an angle at the beginning, they end up at different location. So you see this drift is a sharing of the ellipsoid along the horizontal x-axis, the x-axis, sorry. If you have a lens, and you can go through the same exercise by looking at where the rays are at the beginning and where the rays end up, it's a sharing in the direction of theta. So a combination of drifts and quadrupoles, lenses, will make this ellipse tumble around, and you can use a code to do those calculations. But it gives you an idea what happens when you let particles drift, or when you use a lens. But of course, this is to give you a visualization in your background. If you need the numbers, you will of course do that calculation with the code. So this has, for instance, some very simple, immediately to see consequence. If you have something like here, I call this a focus. Of course, if I show you an ellipsoid, I left out here the rays which are going through that practical focus, which has also an extent in X. But let's say this is a focus, and now you drift. We know already we share the ellipsoid along X. Now you put in the degrader. If you put the degrader here, the degrader make an additional theta change. It doesn't change the position, at least not unless you make a very thick degrader, but let's say a relatively thin degrader, then you will destroy your emittance. The emittance becomes larger, but to this effect. If you would put this same degrader at a different location where you are not in focus, like this, then of course here all the angles change and you have a much larger emittance blow up. So practical consequence, if you have to put a degrader in, be aware that the emittance will increase, but if you put it in the focus, it's the minimum you can have. So put that degrader, if you can, in a focus. That is the lesson from this. Now let's look in real life. In real life, you have a spectrometer, and at the spectrometer, you have a very good emittance measurement device if you want. If you have two detectors, X1, X2, and we have shown here the plot. Horizontally is X1, and vertically is the angle. Because if you have two locations, you can measure the angle. and the computer will immediately show this. If you have done spectrometer experiments, you have seen many of those. And what does it mean? This is actually an emittance, very elongated, because you want it very narrow for high resolution, because the position gives you the momentum resolution and hence the energy resolution. If the focus here is almost in focus at the first place and reconstructed there, so you see the upright ellipses here. You see here a line which goes across at a different angle. That is the kinematic effect. That is an impurity line. Now, if you would focus downstream, then this original line will tilt to one side. If you have your focus upstream, it will focus tilt in the other side. Now, we will reconstruct, we can, since we know this angle and so on, and do these measurements, we can reconstruct by software and make this the projection of all these, which will give the spectrum with nicer resolution. But you could also shift the detector, so it's kinematical shift. Here it is forced by a K-coil in the K600 spectrometer. We'll show that a little bit later. So if you have here a spectrum, then you look only at the X, or the projection of all particles for all angles in X, which is shown here. And you see here the impurity oxygen. Because of the different kinematics, they focus at a different location, not in the focal plane where your reaction you have optimized for, in this case, calcium PP prime 200 MeV, but they will be tilted. And so carbon is in here, and the lower the particle is, the more is the tilt, because the kinematic is stronger. And if you come closer to calcium, then you will have lines. So you can identify to a certain extent which impurity you have, easily to see here oxygen and carbon. Now, this is all in first order, and if everything is linear, but when you take a spectrum like here, you will see it is not so easy. These ellipsoids may end up to be C-shaped or S-shaped, and then you have situations where the focus is not in one place, and these are the higher orders. You also see here, so a third term would be a matrix which depends to the third order on the entrance angle. And you see here also, this is a horizontal plane in the spectrometer here, the angle. You see also if you change the angle, if you change the position, so we make an R radius or momentum dependence or energy dependence if you want, then you have different projections here. So you have energy dependent, which can come because your detector is not in the focal plane, but rotated around the focal plane. So these are higher, the need, I want to show with this that there's a need to deal with the higher orders, because you will have them and we will learn where they come from. This here is the Grand Ryden spectrometer. The Grand Ryden spectrometer goes into saturation at 450 MeV helium-3T, shown here. You do have a strong C-shape X-zeta plots, which means you have here a hexapole. You can correct, of course, but if you project it here by software, then you will see here like dog bones, not so much here, but here obvious, and that comes from multiple scattering from this not corrected aberration. So yeah, you can maybe able to correct, but not to the perfection you want. So we have a need for higher orders. So for that purpose, we go into a Taylor expansion.
George,
yeah.
5 minutes and then.
Yeah. Yeah. Yeah, I have here some more material which I need to go through, but we will then put that into the next lecture, because I think it's important that you get these. But right now we are just... So let me just start the discussion about the higher orders. The higher orders are dealt with by Taylor expansion. So if you see here from a location 1, you go to location 2, and you can do that by summing up the matrix elements. Here, the magnification, the focusing function, and the dispersion, and you can have higher orders. So these are up to second order, so all cross terms. And of course, even higher orders. So if you change not only one parameter, as we have done so far, but you change 2 parameters at the same time, you get cross terms or higher orders. So the higher orders are written in this notation. At the exit, of course, you have still 1 parameter, but at the entrance, you have 2 parameters, here called M and O, so the 1, 2, 3, or the A, X, A, B, or theta, etc. So these are the higher orders, and the code will calculate those for you, as we will learn in the tutorial. The solution of the equation is not what we are dealing with here. Just to mention you can of course solve the movement of a ray through a particle, through a system. You can use ray trace, which uses small slices to integrate through the whole system. In transport, it's usually done by applying simple geometry, but that won't work for higher codes. In quasi-infinity, differential algebraic techniques are used to do this. So quasi-infinity has also the advantage, like ray trace, it can calculate arbitrary higher orders in the way we just felt. So let's end this section with this summary. The ion optics, what is the relationship between the ion optic and the real magnet system? Obviously, an ion optical is meant to describe quantitatively a real magnet system. A well-designed magnet system should have a realistic ion optical model that allows you to plan an experiment and analyze your data. Nevertheless, there will be many limitations that need to be considered and that requires still calibrations of your system. So there's some practical aspect in the commissioning which the code, even if it's as realistic as possible, cannot provide you. Also, the parameters in the system may change, right? Because the code doesn't change, but if alignment changes due to settling of the elements, moving one in, one out, magnet one in, one out, the beam parameters, I mean, you at the entrance of the code, you assume you have some beam parameters, but when the operator comes up, delivers the beam may be different. That is a usual problem. And alignment of the beam. We're not talking about, there are 2 alignments. One is the alignment of the elements. They are supposedly not to change very much, but the beam may come in differently from tune to tune. So you need to talk to the operator, or you need to measure these parameters to know what you're calculating has something to do with what you're actually having. Designing of a system is not what we are really doing here. That would be a next step. But if you design a system for a particular purpose, then more than just ion optical aspects are there, of course, obviously. You need to include the ion optical concept, the calculations of many parameters, often before they are fully known. So you need some thumb rules. If you, for instance, COSI doesn't prevent you to put 2 magnets so close that the coils interfere, that you have to consider. If you are just commissioning, or then the designers have already done that. If you go there, you see nothing interferes with each other, but in the design you have to do that. Detectors and diagnostic systems have to be, of course, included so that you can check what you have and you can learn what your system is. So let's, Hendrik, I think we stop for now.
Very good. Let's give George a hand.